Junichi Horikawa, and this is the 23rd episode for VEX for Algorithmic Design. And today's topic is about the basics of SDF, which stands for Signed Distance Field, a one type of volume you can use in Houdini. And I'm going to show you how you can use VEX to deal with this SDF. I'm going to start by explaining what SDF is, then show what's available throughout this data. Then I'm going to show you how you can modify the SDF directly with the VEX. And after that, I'm going to show you how you can use VEX to use the SDF information for various purposes with several examples. Now let me first briefly explain what SDF is. SDF is one type of a volume you can use in Houdini or in many other softwares. In Houdini, there's two types of volumes. One is the fog type volume, which we have done in other episode for this VEX for Algorithmic Design series. And another type is called SDF, which stands for Signed Distance Field. And both SDF volume and fog type volume uses the same voxel data type. You first have the 3D grid, and then at each cell or at each point at this grid, you have a specific value being applied as a voxel value. But the difference is that the way this voxel value used is a bit different between the fog type and the SDF type. For the fog type volume, for each voxels, it uses different density values to directly visualize it as a density, to use it for something like cloud or fire or a water effect. On the other hand, SDF type volume is used to visualize the surface of a geometry using the voxel value. And in this case, let's say that this is a geometry at the surface that you want to visualize, and by using SDF, you can specifically visualize the surface of the geometry by just using the volume values. So the difference is that for SDF volume, it does not visualize each voxel of its density value, but instead it uses the threshold values of the voxels to visualize it as a surface. Now, each voxel has its numbers applied, same as density, but the way it is being used is a bit different. If the voxel point position is inside the geometry that you want to show as a surface, then the negative value is being applied to each of the voxel values. Now for the points which is outside the surface or the volume geometry, then the positive value is going to be used for those points. And the points or the voxels which is on top of the surface, somewhere around here, you always have the value 0. So when the value is equal to 0, that's where the surface is going to be drawn. And in between the 0 threshold, you have a negative value in inside and positive value in the outside. And that's the rule for the SDF volume value or voxel value. And closer to the threshold, closer to the border, you have a smaller number of negative value for this side. Like let's say this is 0.1, and around here, if it's far away, you have around like 0.3. Depends on the distance, closest distance to the surface, and this will be equal to 0.3. And same for the outside. This one, let's say if this is the distance is equal to 0.3, then A is equal to positive 0.3. So that's what you can get out of it, the voxel values from the SDF type volume. And also there's another data you can retrieve from the voxel point on a SDF volume, which is the gradient information, which is the directional value, which direction this point is going to be attached to the closest surface. So in this case, for this point right here, the closest point to the surface is right here. So what you get is this directional value, the normalized directional value of this vector as a gradient. Let's call this V. And for this point, the closest direction is right here. So this gradient value is going to be retrieved as a gradient value at this point. So combining the distance, which is the value of this voxels, together with this normalized vector, you'll be able to know in what distance these points are from the surface and in which direction this point is being placed to the closest points on the surface. And by having this information, there are several stuffs you can do to use it for several purposes, and that's what I would like to show you today. Starting from how you can check these data values for each voxels. Now let's see how we can do that. Now first thing I would like to show you is how you can check what kind of data you can retrieve from the SDF volume. To do that, I'm gonna start by creating a simple SDF volume first. So I'm gonna first create a sphere geometry. Let's set it as polygon, set some frequency to high so that you have smooth surface. Then let's create a SDF volume using a VDV from polygons. Now VDV is coming from the Open VDV volume, which is a library that you can use to efficiently visualize the volume values, which is a bit different from the original Houdini volume, which only be able to use the fog type but for this Open VDV types you can also use the SDF type volumes. So this is the one that we're going to use today in order to visualize the SDF. Okay, so I'm going to use this VDV from polygons and connect with this sphere. Now, by doing that, you'll be able to convert the polygon into the SDF volume. And if we look at the data type here, it's a bit similar to the volume geometry that we have used previously with the other tutorial sessions. But the difference is that you have now one called VDB and you have a name called surface, which is coming from this name here, written right here. Then you have a number of voxels in X, Y, and Z direction, which is similar to the fog type volume. Now, if you try to create a fog type volume that we've been doing in other sessions, like using an iso offset, and look at the geometry, then in this case you have this volumes type instead of VDV, and you have this name here. Currently I didn't set any names, so the default name is 0, and you have the resolutions for X, Y, and Z. So pretty similar, but this part is a bit different. Now you can still use a fog type volume within a VDB. Currently this is used as an SDF value, but by using something like convert VDB and converting from the SDF to fog, it becomes just like the one you see here, but you still see that this is still a VDV value. Now things you can do with this fog type volume and this Houdini's volume type is pretty similar. You can still use the same volume wrangle to deal together with the VEX without any differences. Only difference is that you can use a vector. You can apply a vector values directly for a fog type volumes in this VDV case. So will become more efficient for many calculations. But for today, we're going to deal with the SDF type. So let's forget about the fog type for today. Now, the first thing I would like to do is to try to see what kind of data you can get out of this volume. And to do that, I thought that the easiest way is to first show each voxels as a point, and for each point, apply an attribute value, which is this voxel values applied in each voxels. and so that you can visually see what the data structure looks like for this SDF type volume. So to do that, I am going to use a volume wrangle. First, let's name this points from SDF. Then what I'm gonna do first is to retrieve the value from each of the voxels, like accessing to the voxel surface, voxel value, which is coming from this one. So as you can see, this is a float value, and by accessing, in order to access to this value, surface float value, I'm using a volume wrangle to access like an attribute like this. Now after I have retrieved this, I am going to try to create a new point at each of the voxel positions using add point 0 at P. Now you can see that the point has been made outside and also inside the volume. Now it's a bit hard to see what's going on inside, so I'm going to create a delete node to delete just the volume after the volume wrangle. So I'm going to select add surface as a group, then you will all be able to see only the points. Now you might have noticed that you get a bit different result using this point wrangle for the SDF type volume. If you use this for the fog type volume, what you'll get is the points for all the voxels in XYZ direction. So in this case, you should be able to have 25 by 25 by 25 points arrayed on the box. But as you can see for this one, for the surface, for the SDF type volume, you only get a point which is close to this surface, the original surface or original volume shape. So in this case, looks like a sphere, and you can see that it might be hard to see, but there's a empty space on the middle of this geometry or point clouds. Now if you try to, let's say, create a ISO offset, create a fog type volume like this, let's say 25 for this one as well, so that you'll get 25, 25, 25, and try to do the same thing. Let's name this surface as well, and try to do the same thing with the same wrangle here to add the point. What you get is all the points scattered inside the box. So you can see, you can already see the difference here. For the SDF, the point is going to be only made close to the surface. For the fog type, it just creates over the voxels, all over the box for each voxels. Now, next thing I would like to do is to apply this surface value to its point as an attribute, so we can check the value as a numbers. So let's do that. Set point attrib 0. Let's name this value at PT, where I have created a point, and as a value coming from the surface voxel value. Now let's check this out by going into the new pane tab, inspectors, geometry spreadsheet to check its point attribute. Now if you look at the points and look at the total number of the points, you have 7,727, which is less than 25 by 25 by 25. And at each point you see those numbers here being applied from around -3 to +0.3. Now where does this number coming from? It is actually the distance. As I said, this is the distance from the edge of the surface, and if it's positive, what this means is that the point is outside the surface, and if it's negative, then that means is that the point is inside the surface. And let's check that out. I'm going to use another delete node, and for this one I'm going to set the entity to point, and let's create some conditions if value is less than 0. and delete non-selected, so only the point in this condition will be selected. And if I say value is less than 0, then the points which is inside the surface is going to be retrieved. So you can see that the surface around here, and you can see that only the points which is inside this sphere has been retrieved. Now if I do value more than 0, then only the points which is outside the sphere is going to be retrieved now, and nothing from the inside. From here we can understand that the surface is at the value which is close to 0 position, 0 value. Now let's also see where does this the range coming from, like from negative 0.3 to 0.3. Now to check that, we are going to select this BDV from polygon, and there's an option where you can change the offset from the surface position, and this is where it is: exterior bound voxels and interior bound voxels. So this determines how much of a distance it's been separated, or been what's the maximum and minimum for the range in offset for the interiors and the exteriors. If you raise up this exterior band voxels, you can expand the voxel values to the outward. If you raise up this interior band voxels, you can raise up the voxels inward like this. And for the interiors, by clicking this fill interior, you can fill up all the voxels with fill up all the voxel values like this without any emptiness. So I think when you try to use this volume, SDF volume, together with the VEX, I think it's a good idea to always check this fill interior from my experience, because it's going to be more useful in many cases. But it really depends on your needs. Now there's another checkbox here, which is called unsigned distance field. If you click that, then the fill interior will be disabled, and you'll left out with the exterior bound voxel, one exterior voxels, which controls both the exterior offsets and the interior offsets. So the one slider controls both offsets. And if you go back to the this detail node, a delete node, and look at the attribute for the point, now what you only see is the positive value. There's no negative value anymore. So by checking this unsigned distance field, you no longer have any information whether the point is inside or outside. You just have the absolute values of the voxel values. It just give you the distance from the surface, and that's just it. Now I don't think it's a good idea to check this on, because it just gives you less information. I think you can still get the same values without checking this one. You just have to get the absolute value for the interior values, for the negative values. So I don't think it's not necessary to check this one if you are working with the VEX. So for my recommendation, when you try to convert from the geometry to the polygon, from the geometry to the SDF, I would recommend checking this fill interior and set a voxel values for the outside offset, and that's just it. Now you can also change this value based on the distance, the real distance on the world space, by checking this command checkbox or toggle. So that currently it says 0.3, which was the maximum value for this geometry spreadsheet for the positive value. So by raising this value up like 1.0, then you'll be able to have the maximum SDF value as 1, a positive 1. Now for the negative value, I'm using a fill inside to automatically fill all the values. So it's going to be automatically determined by the size of the surface. Now currently it says -1 at around -1 as a minimum, but if you change the size of the surface like 0.5, then the interior, the negative minimum will change based on that as well. Okay, so remember that. And it still works for not just for a sphere, but also works for any kinds of geometry. Okay, I'm gonna make this sphere back to a radius equal to 1, and then set the use world space for band. Okay, maybe checking this one, it might also make sense because you can control the distance by you can control the offset by the distance, which I think is pretty useful for the controlling. So I'm going to make this checked on as well, but make this back to 0.3 for now. Now let's also visualize the points based on this attribute, the value, which is this one here. So let's try to do that. I'm going to create to delete, one to show the interior, one to show the exterior. Okay, this one is the interior and this one is the exterior. And let's create a color node. Now for the center, I'm going to use the ramp from attribute and use the ball. And from the exterior value, it is between 0 to positive 0.3, so let's say 0.3, and let's make this reversed. So these, when it is close to the center, it is white, and when it's close to the outside, close to black. Maybe I could change this color to red or maybe blue. Okay. And for the other one, for the interiors, I'm going to use the other colors, and for the range, it is going from -1 to 0. Okay. Now for this one, let's change the color to red to black, and I'm also going to change this range here. So if it's close to the center, you have black value. If it's close to the outline, you have a red value. Maybe I can raise this up a little bit like this, or maybe I can add some inward value like yellow, like this. For this one, maybe I can have like a green or light blue, not sure, maybe green. Okay, now I am going to combine those together and try to visualize it as a point. Okay, so you can clearly see the threshold here, and that's where the point value is equal to 0 or close to 0. Now the next value I'd like to try to retrieve is the gradient value out of the SDF geometry or SDF volume. So I'm going to first duplicate this one, and let's call this gradient from SDF. Now same as before, I'm going to create the points first, then to each of the point I'm going to apply a gradient value that you have retrieved from these point position. To retrieve the gradient value, you can use the function called volume gradient. Okay, and since the volume is coming from the first input, I type 0, and the name of the volume is equal surface. And then you can use a point position, the current voxel point position, as the place to sample the gradient value. And as I said, as I explained, the gradient of this SDF is the direction from the current point position to the surface. Now let's check that out. After I have retrieved the surface gradient, volume gradient, I'm going to store this into some vector variable, since gradient is a vector direction value. Now I'm going to set a attribute to this point, maybe set it as normal direction, like this. Okay, spell mistake, set point at triv. Now let's also delete the volume as we did last time, and let's show up the normal direction by checking this value here. Now a little bit of mistake that I have explained. The gradient value that you get from each of the point is the gradient direction coming from the center of the geometry to outward. So even if the point is outside the volume, it's still facing outward like this. Same for the values inside. All the voxel, all the volumes, all the vector, gradient vector is facing outward, which is close to the minimum, close to the surface, the closest surface point position. So for the volume, for the points which is outside the voxels, it still calculates the minimum direction to the surface, but from this minimum position to the outward points, it creates a direction, a gradient direction. And for the sphere, it just goes omnidirectional. If you try to change this geometry to something more complex, like rubber toy, you have something like this. All the gradient vector is facing outward, this geometry. Same for the inward. Okay, so that's what you get out of this SDF geometry. And using those two values from the SDF, both one for the voxel value and one for the gradient value, you can use a lot of stuff together with the VEX. So let's see what we can do. Now first thing first, as a basic exercise, let's try to visualize this SDF volume as a fog type volume by remapping the SDF values as a fog density value. So let's see how we can do that. Now to do that, what we can do first is to use the same setup that I have right here. So I'm going to copy this one. Okay. And then I am first going to convert this into a fog type using convert VDV, using convert to VDV, and use a convert SDF to fog. Okay. Now this itself should have its specific value for each of the voxels. Now in order to check that out, we can still use the same technique that we have done here. First try to create the points for each voxel surface or voxel points, then check that value with an attribute. Okay, so I have just created the points and set this value that I've retrieved from the surface. Now let's check this out. Now problem with this one, by using the VDV type fog type volume, you don't get the outside point like we can get from the Houdini's volume, normal volumes. So if you like to visualize the outside of the sphere as well, then maybe using the VDV type fog type might not work well. Currently I can only see the positive values from 0 to 1, which is good, but if you want to show the inward or the outward directions value as well, then this might not be a good solution. So in that case, I'm going to use the ISO offset to create a Houdini volume type, the Houdini's normal volume type, and set it to something like 50. Now, by using this one, you'll be able to visualize this as a whole box. If you try to name the volume as density, and instead of the surface, I'm going to say density. Now we'll be able to fill in for all the boundaries of this volume, like this. Now, to bring this SDF volumes value from the SDF value to the fog type volume, which is the Houdini's volume type, you can use the volume wrangle here. So first value you want to connect is the one that you want to modify. So I want to modify this one to convert convert this value from the SDF value, and then connect this BD from polygon to the second input. Now let's say copy SDF value. Now the first thing you want to retrieve is the surface value from each of the point position or voxel position at this volume. To do that, you can use a function called volume sample, which is same as the fog type volume. We have used this volume sample for the fog type volume, but it could also be used for the SDF type volume. Now we want to reference to the second input, then the name of the volume is called surface, and we are using @p, which is the point position of each voxels from this one, as a sample position. Okay, now as a result, you'll be able to get a the value from the surface, and for this one, it is currently checked a fill interior, and the outside is from 0 to 0.3. So the range of the surface value here must be from -1 to +0.3. Okay, so remember that first. I'm going to give a density value for this as value. Okay, so it looks like this. Interior value is from -1 to +0, and then for the exterior it's from +0 to 0.3. Okay, now if you want to remap this into something different, and you can say value is currently 0.1 from 0.3, and then from 0 to 1.0. Okay, but I am just going to keep as the normal value without any remapping for now. We do this later. And I am also would like to retrieve the gradient value as well. Well, maybe not the gradient value, because we don't really need to visualize that for now. So what I would like to do is to visualize this density value that I have retrieved from the surface using something related to the volume, fog type volume visualization. So volume visualization. So I'm going to use this one to visualize its density value. So the minimum of this value is currently -1, and the maximum is 0.3. Okay, now I can then change this diffuse field to a density. Now you can change this color range. Maybe you can change what these setups here, like black body, back grayscale, infrared, two-tone, and so on. Now let's go with the infrared here. Now, as I said, when the value is equal to 0.3, then you get this outside value here, which is right here, because this is a range between -1 to 0.3. So for just for the 0.3 value, I'm going to set it as black. And for the other values, I'm going to keep it as those infrared related value. Okay. Now you have just visualized the surface related value or SDF related value as a fog type volume with the colors. And by changing those expanding values here, let's say equal to 2, maybe I can copy this parameter and paste it to this one here. Okay, and I also realized that by changing this exterior value, you are also changing the boundary of this voxels. So maybe it might be a good idea to get the boundary from this polygon, from this SDF, and then use this as a base for the fog type volume. Okay, now you get something like this. And by changing this exterior bound, you are also changing the fog type volume right here. Okay, and if you change this to 0, then you are starting the visualization from the edge of the surface. Probably setting the edge as black also might make sense, but it's a bit hard to see what's going on here. Okay, I'll just keep it as it is. So that's how you can visualize the SDF type volume with a fog type volume, just as an exercise how you can bring one value to the other. Now, next thing I would like to do is to try to do the basic modification for the SDF value using a volume wrangle using VEX, and how we can use that, how we can do that. Okay, so first of all, I am going to create some base geometry like we did last time. So I'm going to create a rubber toy now as for a bit more complex geometry. And then let's convert this into SDF volume using a VDV from polygons. Okay, and let's set the voxel size to 0.03 so that it can show some silhouette here. Okay, now what I would like to do here is to try to change the values for the SDF using a wrangle value. Okay, and I'm also going to check this use world space for the bound and fill interior. Okay, and let's set the exterior bound range to say 0.3, right, so that you have enough offset. Now let's use volume wrangle. Oops. Then connect it right here, and let's change this to SDF offset. And what I'm gonna do here is pretty easy stuff. I just want to modify the surface value for this voxel, for the surface SDF type volume. Now to do that, you can just say f at surface plus equal to some values like 0.1. By just doing it, you have just created an offsetted SDF value. And by imagining what kind of calculation is being done for each voxels, it's pretty obvious what it's been doing. If you have just added positive 0.1, it might be easier to look at the sketch. So currently, let's say this is a surface, and then the surface value is equal to 0. And if it's outside, then the S surface value is positive, and if it's inside, the surface value is negative. And if you update this surface values by adding 0.1 to its original value, S equals to S plus 0.1, then that means you are offsetting this line to this direction, because let's say if this is the S equal point negative, S equals to negative 0.1, then if you add the 0.1 to this one, then this value becomes 0, meaning the surface, the border of the surface was going to be offsetted like this. As a result, the geometry shrinks, the surface shrinks toward the center of the geometry. So more value you add, more shrink you get. Or if you subtract by a specific value, let's say you subtract by 0.1, then in that case it expands the border. If this point is equal to S equal 0.1, then by subtracting by 0.1, then this becomes 0. Then in that case, this point becomes the part of the surface border, meaning you can calculate the expanding like this. So that's what you can do with this surface modification. By using the addition or subtraction, you can change the border offset. So currently I have just added 0.1 and just shrinked by a distance equal to 0.1. If you subtract by 0.1, then expand the whole surface by 0.1 outward using the gradient direction. Okay, so let's create some parameter for it to control, to see what we can do, what we can see here. Let's name this val plus equal value, and let's set the range from negative 0.3 to 0.3, or maybe 0.2. Yeah, 0.3 is fine. Now, if I move this one, if you go negative, it just expands. And if you go positive, it just shrinks. So this is one of the modification you can use, or you can do with this SDF by adding or subtracting with a constant value like this. Pretty easy, and you can see this offset effect. Okay, now knowing this as a basic structure, knowing this as a basic effect that you can do with the SDF, let's try to expand this information or expand this process a bit with more complex setup. I'm going to try to duplicate this to node, one for the rubber toy and one to convert into SDF volume. I'm going to create another volume wrangle. And this time I would like to try to control the offset using the time-based value, and also based on the height of its point position of this volume, or of this each of the voxels. So let's say SDF, let's say wave offset. Okay, now what I would like to do is to first try to create a value that I'm going to add to each of the voxels as a surface value. And I am going to use the y value based on the y value, which is the height of this voxels, as an angle for the sine function. So I'm going to multiply this point position by pi, which is 180 degrees, and probably multiply by some integer numbers so that you can control the wave numbers. Okay, now I'm going to then use the sine, wrap up with this angle. And as a result, the sine for the sine value, you'll be able to get the value in between -1 to 1. So it might be too big for this geometry, so let's also multiply with some multiplier value. Or this, let's just call this distance. Okay, so now I have two parameters, one to determine the number of waves and one to determine the maximum distance for the wave, or the height of the wave. Okay, now what I'm gonna do is to do the same thing, add the surface value with this value that I've just got. And as a result, you'll be able to modify its VDV value like a wave based on the y position, y height position. Okay, so more numbers you can have for the wave, more waves you can see. And the height controls the height of the wave. Okay. Now, to make it a bit more interesting, we can introduce some time-based value, maybe for the angle. So after this, we can add like time, let's say multiply by 10. Let's make this real time here, so that you can have something like a wavy SDF offsetted geometry like this. The calculation is pretty simple, but you can have a really interesting result like this pretty easily if you know what's going on with the SDF values inside. Now, one thing you might want to remember here is that the SDF is about the rendering the surface. So multiplying for the surface value might not work as you expect, because in order to change the surface border, you need to change its zero value. I offset the zero value in order to change the surface. So by multiplying with any kind of value, you just get, you cannot just offset the value, the current zero values. So if you just want to change its shape, the SDF shape, using the VEX, then most of the cases you need to use addition or the subtraction in order to offset the surface value instead of using multiplication. Now, knowing that as a basic information, let's try to do a bit more complex example using this method in order to create an offset for the surface based on a bit more complex conditions. Okay, so I'm going to copy this one again, and then this time I'd like to use the gradient value as well, not just with the the surface value, but with the gradient to change the surface offset. Okay, so first of all, what I would like to do is to create a bit more high res volume. So I'm going to say 0.01. Okay, now that you have tons of points, 263 by 225 to 242. Now I'm also going to create a VDV smooth to smoothen out this SDF type volume a little bit, maybe by iteration to 4. It's fine, I think. Yeah. Now, and I'm going to set it as mean value or minimum. Doesn't really changes. Oops. Let's just change this to mean value. Okay. Now, what I would like to do is to retrieve the both surface value and the gradient value, and try to use that to offset the surface value for this SDF volume. So let's do that. Volume wrangle and offset with voxel value and gradient. Okay, now let's also check the offset maximum value here. Let me go back here, and currently the exterior bound is 0.3, and let's change this to 0.1 for this example. Okay, so that you have a bit less voxels. Okay, now first thing I would like to do is to retrieve two values. One is the voxel surface value and the one is the gradient value as a vector. So float value is coming from the f at surface, and vector direction is coming from the volume gradient function from the first input. The name of the volume is surface and at p. Okay, now next thing I'd like to do is to retrieve the 2D angle information from this direction angle or vector value. So what I would like to do here is looking from the top view. Let's say from the top view we are looking this shape. Consider this is the face here. Okay, it doesn't really look like so, but consider that. And then for at each of the point, I'm trying to retrieve the gradient information, which should be faced toward the minimum projected point on a surface, going toward the projected point, like this. Okay, and what I would like to retrieve is the angle of each vector is looking from the top. So let's say consider this is the x direction and this is the y direction, and what I would like to retrieve is this theta angle for each of the vectors. Okay, and I would like to use this angle together with some trigonometry to create a value for the offset, and that's what I would like to do here. And I'm going to ignore the upper directional values for this one. So I'm just going to retrieve this 2D angle values out of this gradient vectors that I have just retrieved. So let's see how I can do that. To do that, I'm first going to create one vector value named as, let's say, dir xz, since the planar direction is xz plane, and copy the direction, the gradient direction right here. And first thing I would like to do is to set the y value for this value to be 0 so that it becomes a 2D vector value. Now after that, I'm going to normalize this so that the distance of this vector will become 1. Now I would like to retrieve the angle of these 2D vectors using a function called atan2. So float ang atan2 and dir direction xz dot z and also direction xz dot x. Okay, and probably I might want to get the value in between the mirrored angle. What I mean is that for this vectors and for this vectors, I would like to retrieve the same angle right here. So from 0 to a pi value, meaning 0 to 180 degrees, so that I have a mirrored angle for this one and for this one. To do that, instead of having the value in between negative pi to pi, we can set this x value to absolute value. Even if it's negative, let's forcibly set this to positive. And as a result, you should be able to get a value in between 0 to pi, I think. Now, now that I have retrieved the angle value, I can create a trigonometry-based value using sine function with an angle. And probably I can multiply some wave number as well for this one to the angle. So apply, and let's start with a really low value like 4. Alright, now the sine value gives you a range between negative 1 to 1. So let's remap this first. So fit 1, 1. And for the V, let's set this to 0 to 1. And I'm also going to use the ramp parameter to change the remap based on the curve. Okay, I'm going to create this curve. So currently it's linearly changing. Let's keep that as it is for now, and let's see if I change this later. What happens changing this later? Now, after doing the ramp, we are going to remap this again from 0, 1 to 0 to some specific value or distance, maybe distance. And finally, we are going to update the surface based on this value that I have just created. Okay, now if I raise this up, you can see something starts to happen. Now distance determining how much offset I'm creating based on this angle here, angle value here. And currently I have 4 waves, and the number of waves determines how many this kind of ridges you have. So if I raise this up, you start to see more ridge numbers. This, okay. Now it's a bit hard, it's a bit too jaggy currently, so let's also try to connect a smoothness to BDV smooth, and change this to a, let's say, medium value, because I want to keep kind of a ridge. Let's also set the iterations to 2. Okay. Now, now that currently it's still a volume, so let's also convert this back to a geometry or polygon. So convert BDV, and from BDV I'm going to convert it into a polygon. So polygon. Okay, looks like this. Looks already really interesting here. Alright, now let's also try to change the color based on the surface distance, the distance from the surface. Okay, so the original surface is this one right here. So I would like to calculate the distance between from this original to the updated point position for each surface. Okay, to do that, I'm going to use a point wrangle, reach a point for the polygon, and connect this BDB smooth result to the second input. And then you first of all retrieve the surface value just like we did last time. So volume sample from the second input surface at P, and then update the color value, create the attribute called col using the value. Okay, and the value is the minimum value. The minimum of this value should be related to this distance that I have set here. So I'm going to copy this parameter, then go back here, and let's clamp this based on the minimum parameter and 0. Okay, and I'm going to paste this minimum distance as a minimum value. Okay, and let's name this col. And finally, I'm going to use the color node to use a ramp from attribute for the col, and the minimum range is this value for the distance, and the maximum is 0. And probably I have to set this as negative. Okay. Now let's change this value. Okay, one mistake. I gotta go back to this one and set the minimum to minus min. Okay, now it works. So now you have some gradient value based on the distance from the surface. Okay, and let's change this to some different colors to make it a bit more interesting, like blue and light blue. Okay, looks good. Now let's go back to the offset function here and try to change this curve this time. So if I add a curve here, you start to see some changes on the depths on the surface based on its position. Like this. Right? Like that. And if you try to raise up the number of waves here, like currently it's 10, but if I set it to 20, you have more waves. If you make it less, you have less waves, and so on. So by having the both information with the gradient and the voxel value, you'll be able to create more complex conditional offset like these to make it more interesting stuff. Okay, you can of course animate this if you combine with some time-based value for the angle or something else. Now that we have tried modifying the SDF value directly with the VEX, the next thing I would like to do is to use the SDF as a external information to modify the other geometry. And the first example what I would like to show is the collision detection, which is pretty simple to do. Okay, to get started with a simple collision detection, I'm going to start by creating a sphere. Okay, then I'm going to convert this into a polygon with the frequency equal to 10, and then convert it into VDV SDF, VDV from polygon, and make sure it's checked as distance VDB, and also use world space for a band, and also check in this fill interior. And for the exterior bound, doesn't really matter what the value is here, so keeping it as 0.3 is fine for now. Okay, now I'm also going to create a grid, and let's also show up the wireframe, so smooth wire shaded, and I'm going to raise up the number of grid here. And let's also try to shrink this size of the grid a little bit smaller, like 5 multiplied by 5. and then set the rows and columns to by 50 by 50 so that you have enough points to move. Now what I would like to do is to use this SDF as a guide to create a hole or push this grid as a collided geometry. So meaning I would like to push this grid based on this SDF information toward the gradient direction so that you can have this kind of a hole here, or kind of yeah, hole, I guess you can call this hole. So to do that, I am also going to raise this sphere just up just a little bit. Okay, like 0.1. Maybe a little bit more, like 0.25. Okay. Maybe 3. All right, now what I'm going to do now is what I would like to change the point position on this grid using this SDF value as a guide. So if the grid point is inside the SDF, I would like to move the point so that it touches the surface of this SDF to create kind of a collided geometry. Okay, and you can do that with the information together, combining the value together with the surface voxel distance value and the gradient directional value. So let's name this make hole. Okay, and then first thing first, let's retrieve those two values. One is the surface distance value using volume sample from the second input with the surface at P, and then the directional value using volume gradient from the second input surface at P. Okay, now the first thing I would like to do is to determine if the point is inside the SDF geometry or not. To check that, we can check if this value is either positive or negative. And if it's negative, which means the point is inside the surface. If it's positive, then it's outside. So what we like to do here is to check if the point is negative or not. Let's say negative or equal to 0. And in that case, we would like to move the point position. Now, in what direction should we move here? So let's think about these structures. So currently we have this kind of conditions here, and we are currently looking at the grid point which is inside the sphere. Okay, and we have retrieved the gradient information as well, which is for this point it goes this direction, this point goes this, like this. Okay, so, and we also have the distance value as well for this point, for each of the point. So combining the distance together with this direction, we can push each of the point to the surface, then create this kind of push surface. Now going back to the code, let's try to move the point which is inside a sphere. So to do that, first of all, we need to retrieve the directional value here. And let's move the point by using plus equal, and then direction. This direction is already normalized, so we can just use it as it is. Then multiply the distance, which can be retrieved by this value. And since this is, if the point is inside a sphere, the value is negative, so let's make it positive using an absolute function. Then, and I think I'm missing something as well. I'm missing comma here. Okay, as a result, you can see that I have just pushed the grid points using the gradient information of this sphere. And if I move this sphere up and down, if I move up and down, at some point there's a bit of error here. That is because at this planar position, all the vectors are facing horizontal. So it is as it is. So it's not really like an error. It's just going horizontal. So that's the reason why you have this kind of flatter hole. And if you go down, then you have a different direction. The hole in a different direction, pushing in a different direction. Okay, but as you can see, this is working just fine. All right, so let's keep this like 0.3. And as a result, you should be able to see this kind of a hole. And since we are moving the point in a omnidirection, the resolution of the grid, it becomes a bit low. So if you want, you can then subdivide the grid to make it a bit more smoother. Right. So this is the basic of the collision detection using SDF as a guide geometry. Now keep this collision detection technique in mind. Let's try to do a bit more complex situations. Let's try to use the same technique inside a solver to create a generative hole making pattern. So what I mean is to try to move this sphere by time frame or by frame count. So with some movement and on top of this grid, so it can iteratively move and create a trail on top of this grid as an animation using a subsolver. So let's try to do that. Okay, so I am going to create a copy of these 3 nodes, one for the grid and one for the sphere. Okay, and for the grid, I am going to set the size to 10 by 10 now. And then I'm also going to make this as a remesh geometry instead of the grid mesh. So remesh. Okay, and try to have enough edges or enough primitives so that you have a high-res result. So I'm gonna set the target size to something like 0.15. Okay, looks good. Now for the sphere, I'm going to keep the size as it is, as 1. Okay. And I'm going to move the sphere upward to by 0.5, keep the frequency as 10, and then use this BDV from polygon. And let's set the resolutions to 0.1 as it is, that's fine. Keep use world space band and set the exterior band to 0.3 and fill interior. Okay, that's all fine. Now, and this time I'm going to try to do the collision detection inside a subsolver. So let's create a solver and connect this grid that I want to modify to the first input, and then the one that I would like to animate to the second input, or as a guide SDF to the second input. Now currently this sphere is not moving, so let's try to create some simple code to move this point or move this sphere on top of this grid, maybe like spirally moving based on the time. So to do that, I'm going to create a point, a wrangle before converted into a VDV or SDF. And first I am going to move this sphere in the X direction for each time by adding like time-based values. So add time multiplied by something like 0.2. Okay. Let's also increase the number of time frame to 500, and let's see what happens now. Okay, so you can see that it's slowly moving to X direction. Now, next thing I'd like to do is to move this downward a little bit, but for each frame, so that you have more depths in later frames. So let's say y minus time multiplied by 0.04 or something. So slowly it goes down as well. Now it's a bit hard to see what's going on here because there's no reference here. But if you look from the side, you can see it slowly it's going down. Okay. Now, next thing, I would like to rotate this sphere so that combining all those three transformations, you'll be able to have a more like a spiral movement. So let's first create an angle. Angle is equal to, say, time. And then use the matrix to rotate the point position. So starting with an ident, rotate mate, angle set 0, 1, 0. Now I am going to multiply this matrix to the point position. Now, as a result, you should be able to see this sphere rotating spirally and moving downward gradually, like this. Okay, and what I want to do is to use this sphere positions to push the grid at each frame, using this SDF as a guide geometry or guide volume. And each time I pushed the grid, I would like to remesh it again with the same settings here, so that you always have the same edge for this geometry instead of have to do this subdivision stuff to make it all the surface smooth enough or high res enough. Okay, so I'm going to copy this remesh and let's go inside here, subsolver. And first of all, I am going to paste the the remesh. Then I'm going to connect the volume wrangle. So the point wrangle, since we would like to move the point position of this grid. So point wrangle, connect the pref frame to the point wrangle, and then input 2 to the second input. Then let's name this offset. Now connect the resulted offset to the remesh. Now let's go to the offset and do similar stuff what we have done. Okay, so first of all, we are going to retrieve the surface value using volume sample from the second input surface at P. Okay, and also the direction, the gradient using volume gradient second surface at P. Right. Now check if the value is negative, meaning if the point is inside, the grid point is inside the sphere or not. If it's so, then add the directional value multiplied by the absolute of this value. Okay, and finally do the remesh so that you will be able to have the same edge lengths for the pushed geometry. Okay, now let's go back and see what would happen, and maybe we could merge the original sphere so that we can see in which position the sphere is currently. Alright, so let me maybe set the color for the sphere. Might make it a bit more better contrast, so let's set it as green. Okay. Now if I play it, oops. Okay, seems like, yeah, it's moving, but the sphere is not moving because I have to connect this one instead. Okay, let's do this again. Maybe I'm unconnect this one. Okay, now I see that the sphere is moving, and as it moves, it pushes the geometry at the certain positions and creating this kind of a spiral pattern gradually. So you can see like it's the ball is like creating a trail on the surface of a snow or something. Yeah, looks good, looks great. So that's one thing you can do using this colliding information or colliding technique together with the subsolver to create this kind of a trail, which could be really useful for many cases. Now in the next example, I would like to create a vector field using a SDF. So inside the SDF volume, when the value is negative, if you try to get the vector gradient, the gradient value, inside the point inside this SDF volume, you'll be able to get the direction going from the specific point position inside the volume to the projected or closest point on the surface. And that gradient can be used as a vector field as well. So let's try to do that. First, I'm going to try to visualize this vector field and try to move the point in that direction like an animation. Okay, so to do that, I'm going to start by creating a bit complex surface. So I'm going to use the rabbitoid in this case, as always. Right, and first of all, I am going to convert this into SDF. So convert VDV, and then use not this one, but VDV from polygon. That's what I want to use. Okay, and then let's set the voxel size to 0.02. Okay, and then let's set the use world space for the bound and set the exterior bound to 1 so that you have enough size on the exteriors, right? And might not be that necessary. Maybe keeping this small value might still be okay, but just let's try to do with this one first and then check fill interior. And let's see with this one. Okay, now next thing I would like to do is to use the VDV to smoothen out this shape. So let's do the smoothing with just one iteration, so to keep the overall shape. Okay, now next thing I would like to do is to try to create a bunch of points inside this geometry. So to do that, the easiest way I could think of is to first create a Houdini volume, the Fogtai volume, and then use a scatter node for that volume. Okay, and let's set the number of points like 10,000 to have enough points to animate. Okay, now I am going to use a subsolver to actually create the animation. So solver, and connect the point to the first input, and then for the second input, I'm going to connect this SDF value. And what I'm going to do is that each frame I'm going to move the point to the gradient direction, and as soon as the point touches the surface, meaning the value becomes close to 0, then remove that point and move that point somewhere else, or somewhere in the random position. Or maybe you don't really need to remove, but just move that point to somewhere inside again, so that it can travel again to the gradient direction based on its position. So to reinstantiate or reposition the point, we need a random positions. So at each frame, I'm also going to create a random point scatter with the same number applied here. So I'm going to feed this volume as a guide to the third input for the solver. I'm going to copy this false total count, and let's go inside to write the code. Now, first of all, I am going to look at the volume that I have input and use the same scatter node to scatter the same number of points at each frame. Now, if you just use the normal setup, it's a bit too slow to do this every frame, but by checking off this relax iterations, it'll be much faster. So let's just disable this one for the animation. Okay, now what I would like to do is to move each of the point based on the SDF gradient values. So I'm going to use point wrangle, connect to the point, and then let's move this remap, or let's say move. Okay, and then connect the second input. So this is the SDF, connect this to the second input, and then connect this scatter node to the third input. And for the scatter node, I would like to change the position for each frame. So I'm going to change the seed using the time-based value. So at each time, each frame, maybe using frame might be better. So each frame, the value will change to something different, so that the point scatter will also change its positions. Okay, now, first of all, what I would like to do is to retrieve both a scatter node value as the surface voxel value and the gradient direction. So float val is equal to volume sample 1 surface at P, and then vector direction volume gradient 1 surface P. Okay, first thing I would like to do is to change the point position if the point is close to the surface, meaning if the point's surface value is equal to or more than 0, then move it inside the scatter node or inside this geometry, which is at some point within this scatter node here. Okay, so to check that, okay, where did it go? I thought I wrote the code. It's missing, so let's write this again. So if scatter the surface voxel value volume sample surface at P, and then vector direction volume gradient surface at P. Okay, now if the value is negative, or the positive or equal, then I would like to change the point position. So this means is that the point is outside the geometry. Okay, so to do that, I'm going to retrieve the point position from the third input here. So using point for the third input, P at the same point number. Okay, now I'm going to update the point position to this position. Okay, now the next thing I would like to do is to move the point to the gradient direction. So to do that, I'm going to update point position to the direction value, direction vector with the direction vector, and maybe multiply by some moving speed. So let's create a parameter called speed. And let's start with something like 0.01. Okay, now I'm also going to apply the normal attribute to each of the point, which is coming from the direction. Okay. Now let's also apply some value to the float attribute for this value here, the scatter or the surface voxel value to the point, so that you can have the distance from the surface. And since the point is inside the surface, the value should be negative. Okay. Now let's see if the point is going to be animated within this shape. So if I play it, I can see that the point is moving from inward to outward, and as soon as it touches the surface, it just reinstantiate or reposition its position from one of the scattered point position. So I think it's working fine. Now what I want to do next is maybe I can toggle on this real-time toggle. Now what I want to do next is to color the point based on the surface distance. So let's do that. First thing I'd like to do is to get a minimum value out of the attribute. So I'm going to use attribute promote, and then use for the point val attribute. Let's set the detail. And let's get the minimum, since we're looking for the negative value, since the point is inside the geometry. And let's change this to min val and don't delete the original. Okay, now let's check this out. So in the point wrangle, in the point attribute, you have this val going from negative 0.3 to positive 0.03, which is close to 0. And if you go to the detail, you see the minimum values here as a negative value. So using that value, I'm going to try to color the point. So let's set this to ram from attribute, and then use the val. Then access to the minimum value for the inside the detail using detail expression function, like this, with the min val at 0. Okay, so this is the minimum, and the maximum is 0 in this case. Okay, now, and so it's within 0.3220. So if I change the color here, let's say from red, okay, I think there's some cache. Okay, so if it's close to the core of the geometry, it's close to red, and if it's close to the outside of the surface, then let's say if it's close to, I don't know, black. Yeah. And let's also change the color in between. I don't know, like yellow or orange. Maybe starting from the lighter color to the dark color might be better. How's this? Maybe I'll just keep like this. Okay, and if I play it, you can see the core and the surface clearly. Alright, now I'm going to recreate this point as a line using the normal directional attribute that I've applied to each of the point using this n value here. So let's do that by creating a point wrangle, then create a new point based on the current point position. So at point 0 at p plus at n by some lengths. Okay, and create a line using at prim 0 polyline, connecting the pt num and pt that I've just created. Okay, and the new point doesn't have a color value, so let's also apply the same color value. So set attriv 0 cd to pt with the original color value derived from the point. Okay, set point attriv. All right, and we can maybe set the length longer. Okay, now I can see the animated flow coming from the SDF. Using the SDF gradient information, I've just created the point animations, how the point will travel inside the geometry. Okay, now what I want to do next is to use this as a volume force, a volume vector field, and try to use that as a force field for other purposes to move like external geometry. So let's try to do that, and let's end this session. Now what I'm going to do with the next final example, I'm going to expand what I have done here, try to create a vector field using the volume, a vector volume, instead of just trying to retrieve the direct gradient value to use it for the forces. I'm trying to create a forces inside the vector volume, and together with some optional value applied to that vector field, addition to the gradient value. Okay, and try to use that to move the point again, like this. Okay, so what I'm gonna do, I'm first going to copy all these stuff so that I can create a code based on this one. Then what I'm gonna do first is to first of all create a vector volume using this SDF bound as a guide first. So first of all, I am going to create a bound node connected to this one. Now currently the boundary box is a bit too big, so let's set this extend band to a bit smaller value, like 0.3. I think that's fine. Okay, now I am going to create a vector volume using this bound geometry, so bounding box. So using volume node, and then change this to vector, and let's name this to velocity, and set the default initial value, so the x value is equal to 1, so that I can see what the boundary is. Doesn't really matter what this value is for now, because we're gonna override it in the next step. Okay, now what I'm gonna do next is to copy the gradient value from this SDF to this vector volume using the volume wrangle. So volume wrangle, connect the volume to the volume wrangle, and then connect the VDV SDF from the VDV smooth node to the second input of this volume wrangle. Let's name this SDF copy. Okay, now what I'm gonna do here is pretty easy. I'm just going to copy the value from the SDF to the volume and create a new introduce a new forces as well as addition to the gradient value. to make the force field a bit more interesting, not just going straight forward to the projected point position on the surface, but maybe add some noise value like a curl noise to make it like a turbulence, a touch of turbulence. So okay, so first of all, I am going to retrieve the gradient value from the SDF. Let's name this direction, and volume gradient from the second input surface at P. Okay, and I'm also going to create some curl noise value, curl noise direction. So let's name this C direction using curl noise at P as a guide seed, and probably multiply by some smoothness parameter, and maybe apply some time-based value as well with some speed. And then finally I'm going to multiply the final result curl noise with a scale value. Okay, so how much it can affect compared to the original gradient value. Now, so there's 3 parameters to be applied. I'm going to set the smooth and scale and speed to 1 for now. Let's also change the range for those 3 to so that the maximum equal to 5. Okay, now that I have 2 vectors, what I would like to do next is to add these vectors together to apply it for the velocity value for the vector volume. So V velocity is equal to direction plus C direction. Okay, and probably normalize the result. All right, so that's what I wanted to do to create a bit more irregular vector field, not just by the gradient, but combining with the curl noise. And let's see what it really looks like as a trail. So I'm going to use a volume trail. First of all, scatter some points from the volume, a bunch of points on a volume, and then connect to the first input of this volume trail, and then connect the finalized volume to the second input, this volume trail. Okay, now let's also raise up the number of points to 1,000, 10,000. Okay. Now, it's a bit hard to see the original gradient currently. It might be missing, so let's try to reduce the scale for the curl noise. So this one. So if you try to scale this to 0, then you can see the original gradient direction like this one. And maybe at this point it might be a good idea to use some volume blur to smooth out a little bit. So maybe somewhere around here, and with the really low value like 0.1 to smoothen out the volume. All right, now let's try to scale this up a little bit. Okay, so there should be an original direction being retrieved inside. For the outside, the vector value is equal to 0, so the curl noise is affecting a lot. But actually, we are not going to see this curl noise that much. So maybe scattering using the base geometry might be better. So I'm going to use this scatter point as a trail base. Okay, that might be better so that we can see a bit clearly. And let's set the size of the trail to smaller value. Okay, so now we can see that the trail direction, or the direction of this force field, is mainly going into the gradient direction, but also using a touch of curl noise value. And if I try to increase the curl noise scale, more and more curl noise affection is being applied compared to the gradient. So let's keep this to 1 for now. I think it's a good balance. And if you play this, you can also see the animation played out, and by changing the speed, you can change the the speed of this gradient or the vector field being changed. Maybe I can set this to 0.5. And for the smoothness, if you raise this up, you have more detailed curl noise. And maybe in some case this might be interesting. So let's set this to 3 and maybe the speed to 1. Yep. And scale to, let's say, 1.5. Might give some interesting effect, I guess. Okay. But as you can see, the base direction is gradient, and for the curl noise, I'm just adding it as to give some a bit more noise-based orientation, and create a bit of randomness. All right, so it looks good. Now what I want to do is to use this force field to move the point instead of just using the gradient from the SDF. So I'm going to connect this volume, updated volume, to the fourth input of the solver. Let's go inside the solver and go inside the move point wrangle. Instead of using this volume gradient, I am going to use a volume sample V to access to the vector-based value. So, and I'm going to connect this one, the last input, to the fourth input. So this is the volume vector force field volume, which I've connected to the fourth input. Now, in order to access it, I have to name the velocity volume at P. And that's just it. Go back and show up this line, let's say line. And if I play this out, I should be able to see the line being traveling with a customized force field derived from the gradient, both gradient and the curl noise. Gives you much more interesting movement. Just like this. So this is it for the basics of SDF using SDF volume together with the VEX. I've explained what SDF is and how you can how you can modify the value with the VEX directly. And I have also shown you how indirectly use this SDF information for several purposes. As you can see, there are several benefits using SDF. The information you can get out of the SDF is pretty useful for many stuff, not just limited to what I have shown, but there should be many more practices you can use it for. So if I got enough stock to introduce you, then I would like to show you that as well in some other videos. Okay, so for the next topic, I would like to talk about how you can use VEX to create a basic forces to move geometry or points using a really easy physics based on the easy physics. So that's what I would like to do for the next sessions for the VEX for Algorithmic Design series. So that's it. Thank you very much for watching, and if you like the video, please like the video and subscribe to the channel if you would like to see more videos. And I am also doing the Patreon page myself, so if you would like to support me, if you think my videos are helpful, or if you would like to see more, it would be great if you could support me on the Patreon. You can access to the page from the video description page of this YouTube video. So I really appreciate that if you could do. Okay, so thank you very much, and I hope you learned something new. Thank you very much, and see you next time.